and welcome to our Gas Detection Technologies Overview. My name is Dave Opheim, and I'm a Business Development Manager at MSA. First gas detection technology we'll talk about today is the flammable or combustible gas detection. And as shown in the upper left-hand panel, the first gas detector was a candle on a stick. And this was in the coal mining days. And hopefully you weren't the one elected to clear the methane pocket in the coal mine using this technique. Miners noticed that candles would glow more brightly when they were exposed to methane in the area. Unfortunately, often resulted in an explosion. Canaries were also used, as shown in the upper right, to detect low oxygen conditions in those coal mines. Luckily, that didn't result in loss of human life. Of course, the canary often gave his life up to save the human beings, but it wasn't quite as lethal to human beings. However, because of the problem around gas explosions, the candle on a stick method of detecting gases evolved to a safer implementation, and that is the handheld flame lamp shown at the bottom. And the next slide will give you a little detail into how those are built. So as shown on the left, this handheld flame lamp consisted of a cotton reservoir, a fuel reservoir at the bottom, much like a Bunsen burner, a wick within a gas enclosure, allow the miner to see that flame. And then up at the top, you had a flame arrestor, consisted of a wire gauze and a metal bonnet and a little handle, and that would allow the vapor, surrounding vapor, to contact that flame in the chamber without igniting the surrounding atmosphere. And the photographs on the right show basically how that flame appearance changes as the methane concentration by volume increases from 0 up to 4% in the lower right. And you can see that that flame gets larger and more visible as the methane concentration increases. And remember, this is all below the explosive limits. So theoretically, this would not, the methane around that lamp would not explode. But this is, again, kind of showing you the heat of combustion of methane or hydrocarbons on a hot source like a flame. If we fast forward to today, we offer the users a technology using this whole similar concept, and that's the catalytic bead sensor, where instead of the open flame, we're using a little pellister, a pelletized resistor, which is a hot wire filament, and this active bead or active detector bead, it actually catalyzes or burns the gas molecules in the surrounding atmosphere. There's a complementary bead, or called a compensator or reference bead, that stabilizes this reaction in the Wheatstone circuit. So it compensates for changes in operating temperature, hot to cold, or humidity and elevation as well. It still uses a flame arrestor. Now, this is more of a stainless steel frit, as shown in the bottom lower left corner there. We've got a stainless steel flame arrestor. It prevents the sensor from igniting the surrounding gas should it be explosive concentration. And then the photographs on the right show you those little beads and how actually in the lower right, how it can become really hot, almost red hot, when there are gases present. The benefits of this sensor are that they're fundamentally accurate. The process variable millivolt signal out is linear without any microprocessor. They have a wide operating temperature range and surprisingly good service life. The next slide shows you a little graphic depiction of their signal output. So again, I mentioned they're fundamentally accurate, and this shows you as on the vertical axis the signal in millivolts, the gas concentration across the horizontal, and that the output is fundamentally linear. Usually you calibrate these sensors at the midpoint of the measurement range, roughly 50% LEL, although there is some tolerance there. But the key point here is that depending on the type of gas you're sensing with this sensor, be it methane or hydrogen, you get a lot of signal, comparatively higher compared to like solvent vapors, which can be quite a bit lower. So the key point here, users must calibrate each catalytic bead sensor using the proper gas type for the gas to be detected. And it's also important to remember that these sensors need to be calibrated on a routine basis to ensure proper sensitivity and sensor health. And that cost of ownership actually set the stage for a newer technology that basically kind of leveraged some of the weaknesses and turned them into strengths, and that's the next slide, which is the infrared measurement. And so this slide is showing you the fundamental absorption signatures of different gases and vapors. And on the horizontal axis, we have light wavelength. On the vertical axis, we have the amount or in percent of light absorbed. And you can see that as you look at the different, basically, horizontal signatures, you got water vapor, CO2, oxygen, ozone, methane in the middle, nitrous oxide, and then Rayleigh scattering, which is an atmospheric measurement. And essentially, when you look at the wavelength of the methane absorption, roughly 3.3 microns, you can see that other than water vapor, no other vapor shown here has a significant absorption in that light wavelength. And it's that property that's enabled manufacturers to come to end users with an optical instrument for measuring hydrocarbon gases that is non-destructive. And they're built, basically, I'll show you how they're built on the next slide. So these non-dispersive infrared gas detectors consist of some main components, and they're common to almost every instrument. And up in the upper left, you've got a lamp, an incandescent infrared source. You've got a measurement chamber in the middle where the vapor of interest has to permeate or diffuse into where an absorption occurs. You've got some sensors and with optical bandpass filters, basically close coupled to each of those. And those filters allow these sensors to measure different light wavelengths. The active measurement chamber, active measurement frequency will be is noted by that red filter, and then our offset or reference wavelength of light will be denoted by the green colored filter on that sensor. Those sensors, once there's a signal there, they'll route those signals into a microprocessor where an algorithm is run, and then a gas measurement signal will be routed out to a signal receiver that is proportional to the vapor concentration in the measurement chamber. So basically what happens is that the lamp energizes, it lights up that chamber towards those sensors, and when you have, and again, as I talked about, the filters allow the specific measurement of the light frequencies that we need to measure those gases. And I think I have a little animation here showing you how the gas cloud of interest then permeates into that measurement chamber and allows that those sensors to measure the light level. And what's happening here is that the lower the active measurement channel, the greater the gas concentration. So there's actually a ratiometric measurement going on here. Now it's interesting because you can package instruments using this principle of measurement in two different ways, as shown on the next slide. We can package these instruments in a point configuration, a point detector, where we're using a mirror to reflect the light from the lamp, basically through the chamber and then back through the window to our sensors. And now we can basically have a small, compact, and very, very accurate instrument installed in the field. The other way you can package these is in an open path system. And here the lamp is extracted out of the instrument into a separate transmitter module, and actually it's a much more powerful lamp using a xenon transmitter typically, or xenon bulb typically. And now the energy is transmitted to a receiver module. It can be up to 100 plus meters away, and it's perfect for linear fence line or basically equipment monitoring where you've got a straight line of sight, and any gas cloud in that area intersecting that light beam gets detected, and a measurement variable is routed then to your signal receiver, representing that gas concentration. So that's a quick summary of your combustible gas technologies. The next slide will do a quick comparison of cat bead versus point IR. So with catalytic sensors, you have a lower initial cost. You have a sensor whose one of the key strengths is the ability to detect almost all hydrocarbons and hydrogen gas. But remember, it requires a regular routine calibration in the field because they're not fail-safe. What that means is they can be poisoned by contaminants like silicones and corrosive materials. They do require air for an accurate measurement, so they're not suitable for low oxygen conditions. And because they're destructive, they have to burn the gas to measure it. They have a limited lifetime expectancy, in the best case, 3 to 5 years. Now, point IR detectors have a higher initial cost of procurement, and again, they're not useful for hydrogen gas, but the key benefit here is they're fail-safe. Since it's a non-destructive measurement, they don't have to burn anything. There's no basically high heat levels being generated. They require less frequent calibration, and also they're immune to poisoning. Again, being a non-destructive technology, the oxygen level does not factor into the measurement, so no O2 is okay for IR detectors, and they can be very, very fast because the absorption occurs very quickly. In fact, 90% of full scale, they can be at 2% response time, or 2 seconds response time to that T90 gas concentration. And 10-year warranty is a very common capability because of that reliability. Now, the next slide is going to compare point to open path technology. So point detectors are a very traditional method of detecting flammable gases, and most end users kind of get it, that the point detector's signal, the process variable signal, is directly proportional to the concentration of gas in that sensing chamber, and it represents the gas concentration of the cloud at that point. They are reliant on proper installation to achieve adequate protection, meaning we've got to assess the hazards and identify which gases are lighter, which gases are heavier than air, make sure we got sensors in those proper areas. And as I mentioned, it's easy to understand what that signal means, but point detectors come with a cost of ownership, and it often includes this routine calibration, so compressed gases, testing, record keeping around managing the point detectors. Now, line of sight systems are, again, very well suited for perimeter or linear path monitoring, but the signal output from the receiver module in open path system not as easily understood by end users. It's an integrated path measurement representing the entire or total molecular concentration of the vapor of interest in that light beam. And so again, it has a little bit different meaning, and it takes a little bit of interpretation to understand what that means. The optics, because it's an optical device, without any membrane protection around it, they may occasionally require cleaning. They also require proper installation techniques. They're very basically more rigorous around the installation, since they have to be aligned to one another, and the mounting post or structure has to be solid. So that's a requirement on the pre-commissioning on the installation side, but they don't require routine field calibration. They'll have to be cleaned, but using calibration gas, not required. So that's a real benefit. That's kind of the end of the flammable gas discussion. I'm going to move on now to toxic gas detection, and specifically electrochemical type. So electrochemical toxic gas sensors are a point detector, and using the electrochemical type of sensing technology is the subject here today. And think of these electrochemical sensors as microfuel cells, or if you will, small batteries. They have an electrolytic reservoir with electrodes within that reservoir, and a permeable membrane across the bottom in this case. And they have to be installed, again, where the gas of interest will contact that sensor, and that vapor then will permeate through the membrane and into the cavity, electrolytic reservoir cavity, where a microcurrent will flow across the electrodes proportional to the concentration of the vapor of interest in that sensor. And so typical analytes include H2S, carbon monoxide, ammonia, chlorine. So the signal output then is converted to a milliamp, if you will, from microamps to milliamps, and then routed into a signal receiver like the X5000 shown on the right. Now this transmitter module will provide a digital display to the on-site technicians representing the gas level being detected, and it will provide a signal out as well in either analog 4 to 20 and relay outputs or Modbus to alert other people and other systems of the presence of a toxic gas cloud in the plant. So this is the most common and the predominant technology we see today in toxics. Another way of sensing leaks, especially outdoors, is using ultrasonic technology. And that's the next slide. So this is a microphone-based gas detector. And its strengths include very almost instantaneous detection of a flammable gas leak outside, even upwind of the leak, because it's actually listening for the ultrasonic hiss, if you will, or the ultrasonic signature that's provided by a pressurized gas leak. It's perfect for outdoor settings and for windy settings and explosion-proof or hazardous areas, with the understanding that there are limitations. It won't sense vapors from a liquid spill, or a very low pressure, leak. And also, it cannot differentiate compressed air leaks from a hydrocarbon or a flammable gas leak as well. So there is some limitations, but again, those are often of concern anyway when you have a gas leak. So again, it's another tool in the toolbox to establish another layer of protection. Another technology available today is tunable diode laser detection, and that's on the next slide. So this is a laser-based system. We actually call it Enhanced Laser Diode Spectroscopy, or ELDS, and it's used to detect and measure, very dangerous, in fact, lethal toxic gases in the ppm meter range. These would include ammonia, CO2, hydrogen chloride, hydrogen fluoride, and H2S, or hydrogen sulfide. And again, it provides similar to the infrared type. You've got an enhanced large area coverage using a line of sight system. It can be very fast to respond, and even has the capability of sensing some flammable gases, especially methane, ethylene, and sour gas. But its key strength really is its toxic gas detection capability for these horribly lethal gases, and it's without the requirement of calibration and the ability to protect a significantly large area against these gases, which up till now had to be basically protected using a point detector. So that's kind of it as far as our today's discussion on gas detection. The next slide is going to do a quick summary, with Cat Bead being a point detector for general, flammable or combustible gas sensing. Optical infrared being the next evolution in gas detection for flammable gases in both point and open path configurations using non-dispersive IR for hydrocarbon gases only. That's the limitation there. Electrochemical gas sensors are commonly used for sensing, point detection for specific toxic gases and oxygen depletion. Ultrasonic / acoustic gas detectors are the microphone-based point detector for acoustic sensing of pressurized gas leaks. And then you've got the tunable diode laser, the ELDS gas detector, an open path system for sensing of specific toxic or hydrocarbon gases. There is one other configuration I want to talk about before I wrap it up today, and that's the gas sampling option. And then oftentimes in industrial settings, you have really challenging areas or environments that need to be monitored for a gas leak or a hazardous gas presence. And using, if it's too hot, if it's too difficult to access, if it's just, for whatever reason, it's not suitable for a person to go in there and to calibrate those sensors or to manage that area, we can use a sampling system or recommend a sampling system. And this is basically it's used with a point detector with a vacuum pump. And the vacuum pump using tubing, will extract an air sample from that challenging area, route that sample to a sealed sensor chamber around our sensor. The measurement will occur within that chamber, and then the vacuum pump will exhaust that gas, that sample stream, back to the area from where it was extracted. So it's a way of essentially enabling detection in a very difficult, challenging environmental area. Next slide will basically talk about keys to achieving a high-performing system. First step is identify and follow the best practices around executing a hazard operation analysis and going through scenarios leading to a leak. That's the first thing. And from the results of that study, we can identify the optimal detector placement locations and coverage we can expect from those locations. Once we've got that done, we've got to make sure we've got a proper installation. And that means mechanical considerations and electrical considerations around our detectors, physical installation, our wiring practices around that, our power supply, our power distribution. Once that's done, we've got an operating system without any faults. We can proceed to the commissioning phase and the routine performance test, making sure we've got a high-performing system that's accurate to the national standards, and that we've got a program around performance testing and making sure we've got, we're going to maintain that system. which leads right to operations and maintenance. Do we know how to, do our people on site know how to operate and maintain it and record it, log its performance and log our calibrations and so on, which leads really to training. That's really, at the end of it all, anyone assigned to managing a gas and flame system needs to be trained on how that system operates and how we take care of it, keep it in tip-top shape.